All right, hi guys. This is new for me, and it's probably new for you. So we are going to take a look at Note 6.1, which is rates of change and slope. We're going to take a look at rate of change first and see it visually on a vertical change versus horizontal change. We'll take a look at it as a table. We'll also see it as a couple of points. We'll calculate it as a couple of points, which we'll be talking more. We'll talk in terms of slope there. And we'll talk about slope then as a vertical line, horizontal line, and we'll even take a peek at, we're going to take a look at it as parallel and perpendicular. All right, so let's go ahead and get started with these notes and see how this goes. All right, so we should start by defining what rate of change is. By our book, rate of change then allows us to see the relationship in two quantities that are changing if one quantity depends on the other. Then the following is true. So let's go ahead and write rates of change in here. All right, so we can see that as the rate of change is how much is changing vertically versus how much it's changing horizontally. We can see that the vertical then, we should be comfortable with the idea that that is our dependent variable. You'll have to excuse me with the handwriting. Still new to me writing on this tablet. The horizontal change then is going to be on our x-axis. It's going to be a left and right movement, which is going to be our independent variable. All right. So if we were to take a look at this first example here, it says the diagram at the left, which is a ski lift, which portion is the steepest, and then it says verify our answer. So if we can look at this visually, we're going to ignore this first steep part here, because that could be kind of confusing the question. We're actually going to just focus on the letters that they've given us. So from segment A to B, from segment B to C, and from segment C to D. Which portion of those, or which one of these segments here, is actually the steepest? We can do that visually. We can see that this one doesn't have as much steepness to it as B to C does. And then again, C to D looks to be not as steep as B to C. So we're going to say visually so far, we're pretty comfortable with B to C being the steepest portion. So let's go ahead and write that down. Excuse me. That B to C, or segment BC, is the steepest. Now, we have that. It does ask us to verify our answer. So if we're going to verify our answer, that means that we're going to have to put some numbers to this. Actually pull out some values. And we can do that because they give us the x and y axis. So here's the horizontal axis, and then here's the vertical axis. Again, our x and our y. So this is our x values, our independent values, and these are our dependent values, which is our vertical portion. So we need to find those values, though, for both of these points, B and C. So let's start, because up here we talked about the vertical change being the top part portion of finding our rate of change. So let's look at our vertical change between B to C. So it looks as if B is going to fit right here. Excuse my cursor there. And it's going to be from here. So it looks like our values are going to range from about 50, if I can write this in here, to 90. So that's going to be our change in the two. That's our vertical change. So between 50 and 90, we should all be able to calculate that in our heads, and we're going to get a vertical change of 40. In this case, our units are feet, so 40 feet. And then if we take a look at our horizontal change, so this is how far it's spread apart. So we're changing 40 over this span. And this particular span looks like it's going to be 50. I got to work on that circle arrow thing there. And we're changing to, looks like 80. So we're going to change from 50 to 80, which should be a total change of 30. So we're going to go ahead and write that in here. And this is going to be our rate of change. This fraction here isn't reduced. We do need to reduce this. This one's pretty easy in this case. It's both a division of 10 and both the numerator and denominator. So 4/3 or 4 over 3 would be the way we would need to show that that is the greatest rate of change. And we can go through and calculate the other ones of these, and we can do that fairly quickly, but we won't. We'll just take a quick look at it. If we looked at the rate of change, just to get the idea so they can compare it, the rate of change between A and B then is going to be 10 units. So we're going from 40 to 50 here, so that's going to be a 10. So if we did a quick little calculation here so we can see that, so from A to B, we're going to have a vertical change of 10, and our horizontal change then is going to be from 20, again, excuse that cursor thing, from 20 to 50, which is a change of 30. Again, we can quickly go ahead and reduce this down from A to B, then it's 1/3. So we're going up 1 unit, in this case feet, for every 3 feet that we go horizontally. We can see that this is definitely a much greater rate of change for BC, for segment BC, because we're going up 4 feet for every 3 feet that we cross. And again, likewise with C and D, we can quickly calculate that that isn't going to be as much of a rate of change here. So 4/3, or increasing 4 units over 3 units of horizontal change, will be for our answer for that one. All right, so let's take a look at the next portion of this. There's another question here, and we just did the rate of change versus a visual linear graph, I guess we say, or at least segmented linear graph. We're going to take a look at the next one then, and it's going to have more table values for us, where with the graph we actually had to kind of find our table values, and we could calculate it again, how much we're changing vertically versus how much we're changing horizontally. But this time it comes as a set of values or a table. We've talked in the past that time is usually our independent variable, and you can see here number of days, that's a version of time. And our rental charge here is going to be our output. So our output, or our rental charge, is going to be based off our time. So independent variable for X and dependent variable for Y, which gives us, this is our horizontal movement, our X values. And then this is going to be our dependent variable, which is going to be a vertical change. So this is what we're going to look at first. This left column, our vertical change. So we're going to really kind of look at these values and see if we can figure out how much it's changing by each one of these units. The one thing we need to be careful here with a table, where we could kind of calculate the values looking back up at this ski lift question here, we could see that the rates of change, or the horizontal distance between these, seem to be fairly consistent, and we need to account for that when we do this, especially in a table. We need to make sure that these are either consecutive in their movements. So from 1 to 2 is a change of 1, from 2 to 3 is a change of 1, from 3 to 4 is a change of 1. You get the idea. If this is different, we need to put that into our calculations, because it's vertical change over horizontal change. So these are all 1. This makes it a little bit easier for us. So we can start to look at this. So it says, for the data at the right, is the rate of change for each pair of consecutive days the same? What does the rate of change represent? So in this case, is it the same? Well, let's check it. That's pretty easy to do. We're just going to look at the 2 consecutive days here, and we're going to see what the change is between them. So how much of a rental charge is there between this for running this computer here? So if we have 1 day, it's $60. If we go to 2 days, it's $75. So the change between those 2 days is 15. And we can look at the next set of values. So between 75 and 90 for day 2 and 3. And again, that's also a change of 15. So far, so good. We're pretty consistent. Again, from day to 3 to 4, we're looking at 90 to 105. Again, a change of 15. And then finally, if we look from day 4 to 5, we're seeing a change of also 15. So it is consistent, or yeah, it is consistent. I think that's what it's asking us here. For that at the right, is each pair of the consecutive days the same? Yeah. Is it consistent? Yes, it's the same throughout. And that's key for what we're working with, because don't forget we're in the unit of linear functions. Actually, linear equations is the title. Let me spell that correctly. Let me go back and do that again. So this is for linear equations. Oh yeah, I got to work on that a lot. And for linear equations, we've talked about that before. If this is consistent, it makes it a line. So this is a way to determine if table values are or is a linear function. If these are all the same, or a constant rate of change, that verifies that this is a linear equation. And it is. It's not part of the question, but it's something we should probably talk about. So what does this rate of change represent? Well, it's saying that our values then for increases the same amount. So for $15 per day, that's what it's saying, that for every day that we increase for running this computer, we're gaining $15 of change. So we probably should write that down. Let's write something down here so we have answer the question. So yes, the rental charge increases by the same amount each consecutive day. right, so we've answered that first question. The second question here then says, find the rate of change using days 5 and 2. Well, we know between each single day it changes by 15. We can use any 2 days to calculate this. So that's kind of what this question is getting at. Can we see this between 2 different days? We should still be able to find out or see that the rate of change between these days is still going to be 15. So let's go ahead and write this out. So day 5 then, if we look at day 5, because that's the first thing they give us, we've got a value of 5 and 120. So let's go ahead and write that down for day 5. So day 5, the point would be for the x value 5 and 120 for our y value. Again, that's our x value, that's our y value. For day 2, we can see that we've got 2 and 75. If I can write that correct. Okay, so we're going to use these 2 points to find the vertical change. So what is the change between these 2 time periods? So from day 2 to 5, how much are we increasing? Well, let's find the difference then of y value for day 5 and the difference between day 5 and day 2. So realistically, all we're going to do is take 120 and subtract it from 75. So that's going to give us the change from day 2 to day 5. Now we also need to look at the horizontal change at this point. Now from day to day, it's 1. In this case, we're jumping from day 2 to day 5. So our horizontal change then is going to be the difference between 2 and 5. So again, we'll take day 5 to start minus day 2. We want to kind of keep that similar because we know that subtraction then order matters. We subtracted the 5th day from the 2nd day. We need to do the same exact thing then for the horizontal change. So we subtract 5 from 2, in that case, again, the 5th day from the 2nd day. So if we do this quick little calculation here, we should come up with the fact that the difference between 120 and 75 is 45. And then that's going to be a difference of 3 on the bottom. So we get 45 over 3. And if we go ahead and clean that up and reduce it, simplify it like we should, we find out that 45 divided by 3 is 15. So we find the same rate of change for each point or any points that we can have in that table. As long as it's a linear function, this will be consistent. We could do day 1 to day 1 million, and if we calculate that rate of change, again, the vertical change over the horizontal change, we would still see that it's going to be 15. All right, so if we scroll down here, if I can get this to scroll, sometimes it does, sometimes it doesn't. You can see it's pretty sensitive. So the next question then for this particular situation then, does finding the rate of change for just one pair of days means that the rate of change is the same for all the data? Explain. Yeah, yes it does. And we can say that because the rate of change is constant between all the days, and we can count that. So if it is a linear function, we've had that discussion, it will be the same between any amount of days there, because it's increasing the same amount versus the same horizontal change for each of them. So if the function, make sure I get this right, if the function then is linear, we can say this. Or if it's not linear, that means that it might not be the same between any 2 set of points. So it may be a bigger jump. If this wasn't linear, we might see a change between a certain set of days between 4 and 5. It could be 30. In that case, it wouldn't be the same. We wouldn't be able to calculate it. But if it is a linear function, we should be able to do that, calculate it for any 2 days that we want. Okay, so we've looked at rate of change then in terms of a line, and we've looked at it in terms of a table. Now we can kind of start to create our definition of slope. The slope, if it's going to write here, there it is. So the slope of a line is its rate of change. So if we look at any particular line, we can call it now a slope. We've officially defined slope. We've been teasing it and talking about it, but we've never officially defined it. Now it's officially in our definition set. So let's go ahead and talk about all the different forms of slope and the ways that you see it. These are all different ways to represent slope, so you need to be aware of each one of these. That's why we're going to discuss each. So slope then, again, is its rate of change. Any particular line, again, linear function, it's its rate of change. So we can see that here. And we know that then as vertical change over horizontal change. That's what we've been talking about so far. Another way to describe that, a lot of times, especially when we get a little bit more into linear equations, we'll use the term rise over run. And the reason we'll use that is because we're actually going to graph using this concept of rate of change. We're going to use its vertical change versus its horizontal change, or rise up and down its vertical change over its run horizontal change. And that's the term that we'll use most often. But we also do need to know that it's a dependent variable that's changing vertically, and it's the horizontal or independent variable that's changing left and right. So all of these are terms that you need to be familiar with. Let's tack one more on there. Eventually you'll come to know slope then as m, and that'll be when we get a little bit further along, but we'll kind of tease it around and talk about it so that you're comfortable with it when we actually do use it fully. So slope then, or m, let's talk about how to do this on a graph. So if we're actually given a linear function now, we know that it's a linear function. We can see that from these examples down here that we're going to do in a minute, that we can calculate slope really easily if we're given the graph. From a table, we'll do that next, and we'll be able to see how to calculate it from points. And we kind of did that in the two pre-examples. So looking at this one, we need 2 points to be able to determine slope from a graph. So we need to use 2 points. We're going to do this again. This is a general rule of thumb. You can do this in any fashion, but you have to account if you go from right to left. I always try to make sure that I go from left to right, just to kind of keep the pattern the same. So, and that sounds funny because we're going to be looking up and down, but from up and down, or vertical change from left to right, is how we're going to do this. And it keeps it kind of simple. That way, if you go from right to left, which we will do from time to time, we have to account for the fact that we're doing it that way. So going from left to right, if it's increasing, it's going to be a positive slope. If it's decreasing, it's going to be a negative slope. And that's how we read graphs anyway, from left to right. So looking at this graph here, let me change my cursor. Maybe you can see it. I can't see it on mine. I'll draw a little line on it. So if you look at this graph here, from left to right, as I drew that line, it is increasing. It's going up to the right, to positive infinity. If we take a quick look at this one, as I draw this line down here, it's decreasing from left to right. So that's just a nice way to keep that. So we'll always kind of look at this from left to right. So let's do this quick calculation here and see if we can find out what the slopes of these lines are. Maybe we won't do all the examples, but we're going to use the concept of rise over run for this one. So I'm going to write that in right here. So rise over run, again, is going to be our rate of change. And I think I wrote rum there, but I think we're okay with what that means. So I'm going to actually equal this out as rate of change. And because I'm writing on this, I don't write as well, so I'm going to try to shorten things like that. So rate of change is the rise over run. So to do this, we need 2 points. You really should use grid points only. So looking at this one, you can kind of see, let me switch this over and do a different color, red, so we can kind of see it. So right here, we're going to use this point and this point. Don't try to estimate slope. If you have to, if that's all you've got, then that's fine. But in this case, we're just going to take 1 point. Again, going from the left point, like in the rules that I gave you there, we're going to go from the left point to the right point. So how far is it changing from the left point to the right point? Well, let's check the rise part. And then you can see in this example, it's already written out for us. So we're going to go up 2. So our rise then is 2. And our run, which is going to be our horizontal movement from this left point to this right point, is going to be over 1, 2. I'll mark it off so you can see it. So 1, 2, 3, 4, 5. So we're going over 5. Oops, I drew in the wrong spot there. But 2/5, or a rise of 2 over a run of 5. So that's the vertical change, or the rate of change for that particular line. So let's do that again for this one over here, example B. Again, starting at the left point, I gotta work on how to get that circle thing out of there. Going to the right point. If I take too long drawing a spot, it doesn't work. Again, going from left to right, we're gonna do this. So we're going to look at how far we're changing. But this time you'll notice that we're not moving upwards to go to the other point. We actually have to move down. So we need to account for that. Down is a direction. A direction is usually determined by a negative or positive sign. So in this case, if we're moving down, this is going to be down 1 or negative 1. We're moving down 1 unit. So 1 unit down. To go to this other point then, we're also going to go to the right. This point could be over here. There's no reason it couldn't be to the left, but it doesn't happen to be in this case. So we're going to go over and count these units. So 1, 2, 3, 4, 5, 6. So we went to the right 6. It is a positive move to the right. So I know we're doing blue there. You can kind of see the red and the blue. Maybe that's nice for you or not. So we went down 1 in a negative direction, and we went right 6 to get this slope. So our rate of change, or slope for this one, is going to be 1 over 6, negative 1 over 6. So again, that's going to be our slope. We can write or we can write rate of change, just getting familiar with the terms. Let's do another quick one here. Looking at this line, it is decreasing. So let's find 2 points. Again, it doesn't really matter which 2 points because it's going to be the same, but we need to use grid points. So let's use these 2 points here. Again, going from the left point to the right point, I'm going to go down 1, 2, 3, it looks like. So down 3, so it's going to be a -3. And I'm going to go over 1, 2, 3, 4 for this one, so it's right 4. Again, if I had gone to the left, I need to make that negative also, but I didn't. So whatever unit, so if you're going down, it needs to be a negative change. If you're going up, it needs to be positive. If you're going to the left, for whatever reason, and we will do that, it'll need to be negative, or if you're going to the right, it needs to be positive. So keep track of your directions. Again, that negative sign and positive sign is a term of direction for us. So let's scroll down to the next part here. All right, so now we're going to do this slope. We're calculating slope instead of actually counting it from a graph. Let's assume that we don't have a graph. You can see in the examples we're about to do, it says slope from 2 points. They didn't give us a graph. Could we put these on a graph and count the rise of run? Absolutely, and that's probably a good way to go. But we can do it quicker if we just do a quick calculation. So if we're given 2 points and asked to find a slope, really we're going to do the same thing we did before. We're actually going to take, and if we go back up here and kind of see these values, we're finding the difference between the y value of the left point and the y value of the right point. And it's just the difference of. That's really what we're doing. So there's a quick little formula for slope, if I can line this back up, which is y2 minus y1 over x2 minus x1. You'll need to know that. It's one that you'll need to memorize. I may give it to you for the quiz for the first part, but overall, you should be pretty comfortable and familiar with this. So get very familiar with that equation. y2 minus y1 over x2 minus x1. It doesn't matter which point you use to do this. It just matters that you keep the same pattern. A lot of times I'll actually ignore this and just make sure that I use the same direction. So if I take the very first point that they give us, A, and I subtract my y value from the b value, as long as I do that same order, I subtract the x value, so I'll actually write as I talk. So if I take the x and y values here, let's write them in. I'm in red. I should probably change that back to black. They like to, as long as you do it in the same pattern. So if you always work from left to right, it works. And I'll explain more of that when I'm actually back in class. But for today, let's follow this this little formula here. So we need to label these. This is going to be our first point, so we're going to label it 1, and that's y1, and this is x2 for our second point, and y2 for our second point. So now we can go ahead and calculate this slope. Again, just finding the difference between the y's and finding the difference between the x's. Again, vertical change over horizontal change. So bear with me while I find my pointer. I'm going to change this back to black. All right, so I'm going to go ahead and start to write this out. So I'm going to take my y2 point, or 7, and I'm going to subtract that. Again, up here, you can see where I'm at. I'm going to subtract that from my y1 point, which is 1. Pretty simple so far. So I'm going to put that over, again, x2, or 5. I'm going to write that in here. And I should subtract, it's the difference of, but notice that this is a -2. We need to keep that. We can't use that, we can't lose that negative. It has to stay with it. And a lot of times this is a point of contention, a part where students will make a mistake here. We need to use parentheses. It's probably the best way to decipher this. So I'm going to put that in parentheses. So it's 5 minus a -2. And we know that 2 negatives make a positive. So that's really what's going to happen there. We need to add 5 and 2. So if we do this calculation, 7 minus 1 gives us 6, and then 5 plus 2, because 2 negatives make a positive, we end up with 7. So our vertical change is 6 units up and 7 units over. No negatives left over in that one. Okay, so let's do one more with quick calculations of these. And this time, instead of labeling the points, I'm just going to show you what I do, which is do them in the same order. So I'm going to take and subtract from this C point from this D point. And I'm going to do that for the Y values, and then I'm going to do it for the X values. So I'm going to take 5 as my first Y value, and I'm going to subtract it from my second Y value, which is 7. Again, as long as you do it the same order from left to right, it doesn't make a difference in the calculation. The slope will come out to be the same. So now I've got to take this X value for C, which is 2, and I got to subtract it from the Y value, or the X value of the D point, which is 4. Okay, so I'm going to do this calculation. So 5 minus 7 gives us a negative 2. Don't be worried about that negative. That's perfectly fine. And then we've got a 2 here minus 4. Again, don't worry about that negative. It's perfectly fine. So we end up with negative 2 over negative 2. And we just saw over here in the previous problem that two negatives make a positive, and 2 over 2 is a fraction that reduces nicely into 1. So it's hard to write, or I guess conceptually understand. That's a terrible one, but we'll keep it. No, we're not going to keep it. I'm going to erase it. Slope of 1, it might be easier to understand if we write it and keep it in terms that we're familiar with. So its vertical change is 1, its horizontal change is 1. It just means up 1 over 1, up 1 over 1, up 1 over 1. You can write it as 1, and that's the understood part, because every whole number is a fraction by putting it over 1, and we've talked about that in previous classes. All right, we're in the home stretch here. We're going to finish up with talk of a couple special cases of slope, one of which is the horizontal line. The slope for a horizontal line is 0. If I get it right again, there is no slope. It does technically have a slope, it's just 0. There's none there. So a nice horizontal line is 0 slope. So any line like that, you have to memorize that. These are things you want to memorize. I'm going to write that down. Memorize. You need to memorize these because these are point of contention. A lot of times there's questions like this on the MAT, SAT types of tests that we take, and so you want to make sure that you do know these. They do like to ask about these special cases. The slope of a vertical line then, if this one's 0, is undefined, meaning it actually technically doesn't have a slope. I did put a little note down here, the speedometer. It's kind of tricky to do by video, but if I can do it really quick, and it's a good example for me, but I can't find a good picture of a speedometer that actually functions this way. The way I think about it, when you start out and you're in a car and you're starting to drive, you're going 0 speed, so your speedometer is horizontal. You're going 0 speed. Okay, so if you can imagine this big speedometer like this. So here's speedometer. I'm going 0 speed. Most of them kind of point down to the corner, but let's just assume the speedometer has 0 as a horizontal straight across. So whatever speeds I'm going, then I speed up and I'm going 20, 30, 40, 50. Let's say I top the car out at 70. It's an old car. It doesn't go very fast. So let's say that it tops out at 70 miles an hour. And let's say that that's somewhere over here. Now, your speedometer, though, if you've ever been in a car and you go really fast, and let's be honest, none of you ever will or ever should, because that's super dangerous. I'm not condoning that by any sense of the matter. But let's say that you do go really fast. Eventually, the speedometer goes off the numbers. It actually passes the numbers, and you can't see it anymore. So you really don't know how fast you're going. So let me change the color of my pen here. So we'll say that's over here. Oops, there's a little line. So we'll say that we go off, and it's usually somewhere towards the top. Again, most cars nowadays go really fast, so a lot of times the speedometer is somewhere over here when it goes off the scale. But let's just assume that this is a simple speedometer, and there's 70. We've passed it, and now we're vertical. This is a vertical line here, this little red line. This is vertical, and we're off the scale. We technically don't know how fast we're going. That's how I remember. For me, that was the first way that I remembered the difference between horizontal and vertical line, or vertical slope. If it's vertical, I'm off the speedometer. I can't read my speed, so I'm going undefined speed. If I'm going nowhere and I'm not have any speed, any rate to mine, it's horizontal. So that's how I remember that. I kind of remember speedometer. 0 speed, 0 slope, 0 goes with it. And then if I'm going too fast, I'm off the top, I'm vertical, I have no defined speed. Again, no defined slope. So you can take a look at these. These are pretty quick and easy. So if this is a horizontal line, it has 0 slope. Again, I'm going to use that term of M, even though we haven't officially defined it. Here is the vertical line. Now let's actually test this so you can see the slopes. I didn't do that here. Let's go ahead and calculate it. We know that we can go ahead and take our vertical change, and that's because it's a line. We could do the 2-point thing that we just did with the y2 minus the y1 over the x2 minus the x1, but let's keep it simple. What's my vertical change between the left point and the right point? Well, it's none. They're both on 2. They're on the y-axis of 2, so there is no change. 2 minus 2, if you really wanted to do that, is going to be 0. So that's my vertical change for this particular horizontal line. There is none. And now if I look at the horizontal change, I'm going from 1 to 2, 3, 4, it looks like. Actually, it's right there. Good job, Mr. Hallam, looking at the numbers. So I'm moving from 1 to 4, which is a 3, but any number that's divided by, or I'm sorry, any 0 divided by any number is just 0. So you can see that it confirms the fact that a horizontal line should have no slope because there's no vertical change, which means it's 0, and it'll always just be 0 as a result. So let's take a look at this vertical line. Again, this one's going to be undefined. We just talked about that up at the top. This is giving me a little trouble. So m equals undefined. I'm going to just put UND for undefined. Now let's do this quick calculation again. So my vertical change from the left point, which that's hard to describe because there is no left point. We'll just do the one at the bottom. It's fine. Any point will work. So we're going to go vertical change of 1, 2, 3 units up. And so we're going to put 3 there. And then our horizontal change this time, since it's both on 4, there is no horizontal change, so that means 0 horizontal change. Well, any number divided by 0 is undefined, and you can put that in your calculator to confirm that if you don't trust me. It will give you an error message. So that's why 0 slopes are horizontal lines, and that's why vertical slopes are undefined. So now that we've got that taken care of, I think we're in the home stretch. I know these videos a little bit longer than I planned, so I'll keep this part quick, but we do need to talk about parallel and perpendicular lines because that deals with slopes. For parallel lines, and I think we're all comfortable with what a parallel line is, a parallel line then, or two lines that do not intersect, have the exact same slope. And you probably figure that out on your own. Because they never intersect, the slopes, the steepness is the same, and we talked about that in that first unit there, so that's something we're fairly comfortable with. With perpendicular lines, though, this will be slightly new if you didn't get it in geometry. Let me spell this as I talk. It's a little bit harder to do. that's supposed to be a C-U-L-A-R. Perpendicular lines then have a slope that is what we refer to as a negative reciprocal. Now this definition that they give us is not very clean, so we're going to make our own little definition right here. So a negative reciprocal. Let's read this definition they give us from the book and see what we get out of it. So it says, in a plane, two non-vertical lines are perpendicular if and only if their product of their slopes is, I think we have to put in there, -1. I don't know if we've talked about that a lot, but if you take the negative reciprocal, we know that if we multiply by the reciprocal, it takes any fraction and it turns it into 1. We've used that before when we were doing one-step, two-step solvings. If we use a negative reciprocal, it should make it a -1. So that kind of makes sense. And that's what we'll see with these perpendicular lines. It's worded in the terms that if you took the two slopes and you multiplied them together, that they would turn into a -1. So for example, let's say we had a slope of 2 over, well, we can't use 4, so let's use 2/3, because 2/4 we'd have to reduce. So let's put a 2 over 3. That's our slope that we're talking about here. So the perpendicular slope of it would be, ready? Flip it. That's the reciprocal part. So I'm going to flip it. And then it says make it negative. So there's a negative. And then this right here says the product of those. So that's where this multiplication sign comes from. So if I took 2/3 and I wanted to check to see if -3/2 is the perpendicular slope to it, meaning that the line with this slope -2/3 meets at a 90-degree angle to this line that has a slope of, I'm sorry, -3/2 meets with this line of 2/3, they should meet at a 90-degree angle. So if they come out to be -1, and that's what we're going to do. So we multiply fractions, multiply numerators, multiply denominators. So 2 times -3 is -6, and 2 times 3 is 6. And you can see that that's going to simplify down to -1. So that's the only case that you can confirm that something has a 90-degree angle or that they meet at a perpendicular, that they meet and that they're perpendicular, as if their slopes are the same. I'm going to spare you the concept of going through that because we just chit-chatted about it. So same slopes for parallel, perpendicular is negative reciprocals. And that's really just introduction. You'll do a lot more of that later on with some of the other terms that we do, and you'll do a lot more of it in algebra too. So here's your homework day 2, page 286, the odds 1 through 41. Most of them are pretty quick and simple. You should be able to complete a good portion of them in class. So hopefully this was not too bad. It's my first time through, so hopefully it wasn't too boring. Hopefully you could read it. But yeah, feel free to share your